So today we are going to take a look at factors of polynomials. Mainly we are going to take a look at remainder theorem and factor theorems. Remainder theorem tells us that if fx is divided by x minus a, then the remainder is going to be fa. What does it mean? If you have a function, call it fx equals to x to the power of 3 minus 2x squared plus 3x minus 4. If you would like to divide it by x minus 2, traditionally you are going to conduct it using long division, and it is going to be taking a lot of time and a lot of attention would be needed, because you may make careless mistake for you to figure out this remainder or the quotient. So rather than doing this, we can basically just substitute the value, and the value we are going to substitute is going to be the a value. In this case, because we are going to divide it by x minus 2, so we are going to substitute by the values of 2. So f2, when you substitute f2, you will be able to get 2. So you can conclude that the remainder of this particular functions divided by x minus 2 is going to be 2. Then we have come into factor theorem. Factor theorem suggests to us that if you have fa equals to 0, which means if you substitute 1 in this particular case into the equation, if it does gives you a value 0, then it's a factor. And let us test it in this particular case. 1 to the power of 3 minus 2, 1 to the power of 2 plus 3, 1 minus 4. You will then get 4 minus 6 equals to negative 2. In this case, substitute value 1 into this equation does not give you 0. So s minus 1 is not a factor of fx. Right? So if it does give you value 0, then it is a vector of fx, but in this case it is not. So we're just going to move over it. And then there are several different other methods we can use to find the factor of polynomial, such as observations. So we can use potential values as substitutions. If it satisfies the factor theorem, then we can say, yeah, it's a factor, or you can also use long division. So in this particular case, we are going to use this as an example. We were told that it is a factor. So how can we assure that it is indeed a factor? First of all, we can substitute 2 into the equation of 2 to the power of 3 minus 4, 2 to the power of 2 plus 5, 2 minus 2. So this is 8, this is 16, this is 10, this is 2. So we have 18 minus 18, which indeed it gives you value 0. So from here, you will be able to tell that x minus 2 indeed is a factor. So this statement is valid and is true. And we will perform long division. So x to the power of 3 minus 4x to the power of 2 plus 5x minus 2 divided by x minus 2. X to the power of 2, x to the power of 3 minus 2x to the power of 2 minus 2x to the power of 2 plus 5x minus 2x minus 2x to the power of 2 plus 4x, and you will get x minus 2 plus 1, x minus 2. Indeed, you do not get any remainder after you perform the long division. So we can safely say fx can be written in terms of a cubic form. It can also be written as quotient as well as the factor. Right? So it can be broken down into a simpler, more able to solve form, and then you can further break it down into x minus 1 perfect square, x minus 2, and so this is the complete factorization of fx. Solving cubic equation. So again, if you have questions like this, you can then solve it. Use factorization method we have learned from the previous pages. You can then equate it to be 0, then you will be able to get some of the x-intercept, or so-called the solutions or the root for these cubic equations. You can then use it perhaps to draw a graph or to figure out whatever the question wants you to figure out. So the key takeaway from this particular chapter is remainder theorem, factor theorem, long division, and you can use long division as well as factorizations to solve cubic equations. Thank you very much for listening. Do not forget to work on the additional reading material.